Section 5.1, sequences. So sequences are numbers that go in a specific order. So it's not just the numbers, it is the order in which the numbers occur too. And we should be able to find some sort of pattern. So if we look at this sequence, it is the powers of 2, and we could also represent it with some sort of general equation, where again we've got that kth value of that sequence. So here's how we're going to express these in general. We've got the little subscript, and those are the terms. So we'll have generally an initial term, we'll have a final term, and again we can have both explicit, and as we'll see later, recurring formulas in order to get these sequences. So let's practice finding terms of a sequence. So a sub k is k over k plus 1, and you'll notice we're being told to start at k is greater than or equal to 1. So I start plugging it in, and as you can see, here are the first 5 terms of my sequence. B, I've got I minus 1 all over I, but here you'll notice I'm going to use I is greater than or equal to 2, so that means for B I start with 2. And if you look at these, I do actually get the same first 5 terms for both of them, but again, the formulas that generated those were different. We also have something called an alternating sequence. So here, if we take -1 to the j, for every integer j to the 0, as you can see, we're going between -1 and +1 for each of these. And we also say it oscillates, meaning it just constantly goes back and forth between those two values. There's nothing else that we're going to get. So let's take this sequence and see if we can find a formula for it. So how do we go about doing that? Well, we start looking at the numbers. Do I see any patterns there? Well, first of all, it's going plus, minus, plus, minus, plus, minus, so I'm going to notice that. The other thing I'm noticing is the denominators appear to be perfect squares. So I'm rewriting a little bit because I'm hoping to see a pattern. So I'm going to have definitely k squared on the bottom, and then again the top is going to be either positive or negative. Well, is it positive for the evens or positive for the odds? So here we start it with an even. So if we start at 0, I'm going to have it to the positive k. You'll notice, though, that that makes my denominator k plus 1. If we start at k is 1, though, so that my denominator is just nicely k squared, because I want to start with positive, I've got to have that exponent as k plus 1. So it does matter where we start. That is going to change how we write that formula. Right. Let's also talk about sums. The notation is this letter, that is the capital Greek letter sigma, and we'll have something on both the bottom and the top. So I would read this as the sum of a sub k from k equals m to n. So we have the sequence of numbers from m to n, but instead of having them just terms, I'm going to add all of those terms up together. So here I've got a1 is -2, a2 is -1, a3 is 0, a4 is 1, and a5 is 2. Let's find the following sums. So this is the sum of a sub k from k equals 1 to 5. So in other words, I've got a1 plus a2 plus a3 plus a4 plus a5, at which point I throw in my values, and I'll get out 0. My next one, I've still got the sum of a sub k, but I'm going from 2 to 2. So in other words, I'm only going to have a sub 2, which happens to be -1. Number C, you'll notice my subscript now is a sub 2k. So I'm going to plug that in. I'm going to end up doing a sub 2 plus a sub 4. So we're only using 2 of the values. And as it happens, they do add to 0 anyway. But we can change that subscript as well as other things. And again, there's a lot of different ways we can express these. So we would call these formulas as well as a sum. So let's say we'd like to compute this summation. So again, let's figure that out. That'll be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is going to get me 55. Now, all the problems we've seen so far, we've had a number on the top as that upper limit, but we sometimes see a variable as well. So here, I'm only going from I equals 0 to n. So generally what we're going to do there is we'll do the first 3 or 4 explicit. So you'll notice I've got the 0, 1, 2, and 3 term. And then I've got plus, dot, 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 plus, and then I'm going to go ahead and express that n term. If you can simplify the n term, definitely do so. And as you can see, we went ahead and simplified those first 4 terms as well. Let's go the other way. So now I've got some terms, and I would like to write that using that sum notation. So again, ideally I would like to have each term written in the same form. So I've got 1 over n plus 2 over n plus 1 plus 3 over n plus 2, and so on. So here I'm using I as my variable. So I'm going to write that as n plus I on the bottom and I plus 1 on the top. And I'm going from I equals 0 to n. So again, we are looking for patterns. And we do sometimes have to do a little bit of rewriting in order to see those patterns. So we call that top a free variable. So again, we can have an actual number there. We can also have just a variable, but that lower bound, we are generally going to see an actual number there. All right, so let's find some values. So here I've got 2 to the 0 plus 2 to the 1 plus 2 squared, all the way up to 2 to the n. And let's find that when n is 0, 1, and then 2. So when n is 0, again, I'm going to plug those in and run it out, but I'll only have the one term because we start with 2 to the 0. So I will just get 1 there. Now, once I get the other ones, I will actually add a few out. So if we're going to 1, I'll have 2 to the 0 plus 2 to the 1. I'll get 3 there. And similarly, I'll have 2 to the 0 plus 2 to the 1 plus 2 squared. And then similarly, add those up. We're also going to see problems where we might have more than one thing going on. Now, there's no parentheses here. So it's only this 2k that I'm taking a sum of. This other term is not part of the summation, and I'd like to grandfather it in. Well, if we expand that summation, you can see that it does go all the way up to 2 to the n, at which point my next term is just 2 to the n. So to change it, I've still got 2 to the k here, but now my top is n plus 1. Let's say we want to separate off a term. So here's my sequence or series, and again, I'm generally going to run out a few terms so I can see it. So I'd like to break off that last term. I want to have it separate. And at this point, I'm just going to then have 1 over I squared and go to just n. Let's talk about a specific type of series, which is called a telescoping series, and these are generally in the form of 1 over k minus 1 over k plus 1, or we can express it as the sum of 1 over k times k plus 1. Well, what happens if we run a few terms out on that? Here you can see we've run out a few terms, and then we've got the last 2 as well. I get a negative 1/2 here, but then I immediately, when I start the next term, I get a positive 1/2. And similarly with the 1/3 and the 1/4 and so on. So in other words, everything crosses out except the very first term and the very last term. And so that sum will always simplify to just that. It's a special property. We've looked at sums. Let's look at products. Our product notation, we're going to use that capital Pi. And Same idea with the sum. The only difference is now instead of adding, I am multiplying. And again, otherwise everything is going to be pretty much the same. So let's do this product. So I'm going to go 1 times 2 times 3 times 4 times 5, and I multiply them up to 120. Similarly, if I plug in this equation, k over k plus 1, here I'm only going from 1 to 1, so I have just the one term. So my answer is just 1/2. Let's talk about some properties of both sums and products. So if you've got two sums that are added, assuming the lower and upper bounds are the same, you can write them all together. If you have a constant, you can pull that in or out of a sum as need be. And with the product, once again, you can multiply them, again, assuming that those bounds are all the same. So if we want to simplify these, you'll notice for number 1, again, my bounds are the same, and I'm adding, so I can basically write it as the a sub k plus 2 times the b sub k, and at that point, I am just going to simplify that algebraically to get 3k minus 1. Similarly, if we take the products, I can combine them, so I've just got the a times the k, which simplifies to k squared minus 1, and again, I still have that product notation out in front. What happens if we want to change a variable? So as we've said, there might be more than one way that we can express the same thing. So we could go from 1 to 3 of k squared, or 1 to 3 of I squared. Those are exactly the same, and I can write them however I feel like. Sometimes we want to change a little bit more than that, and this is where we're going to put in dummy variables. So let's say I've got j minus 1 quantity squared. I'm going from 2 to 4. Well, if I run those numbers out, that's the same as 1 squared plus 2 squared plus 3 squared. So I'm going to change my variable, just so that there's no confusion that I'm not using the same thing, and write my summation a little bit more simply. And there is the change variable that I made to do that. Again, here's a little bit more detail with that same problem. Again, we are being very precise here about what we're doing so that you can see how we get from the one to the other. Now, we've seen this before where the upper in particular might have a sum in it. So for this one, let's try writing j is k minus 1. So not only do I have to change it in the actual problem, I have to check both my lower and upper bounds. So when k is 1, then j is 0, and when k is n plus 1, j is going to be just n. That gives me my new bounds. And similarly, I'm going to substitute into the actual equation, and I will get the sum from j is 1 to n of j plus 1 over n plus j plus 1. But these are going to give me the exact same values. Last, let me hit the factorial notation. It looks like an exclamation mark, and that means we are multiplying down. Do note 0 factorial is 1. So here's a few. So for example, 3 factorial is 3 times 2 times 1. 5 factorial, 5 times 3 times 2 times 1, and so on. I am not going to worry about this choose R, so we are going to skip that. The only thing we need to know how to do is simplify with factorials, and as you can see, I am expressing them differently. So for 8 factorial over 7 factorial, I rewrote 8 factorial as 8 times 7 factorial so that I can reduce. And as you can see, I am doing similar reductions for my other properties.